stuff.
All right, and next speaker is Andy Neitzke from Yale to tell us about some geometric applications of exact WKB.
Yeah, so I'd like to thank the organizers for the opportunity to come and speak at this, this really excellent, inspiring workshop. So my title is some geometric applications of exact WKB. So realistically, it'll be one geometric application of exact WKB. And so everything that I say is going to be pretty old. So this is an account of some program that started in joint work with Davide Gaiotto and Greg Moore. And if I would summarize it kind of in 2 sentences, I would say, well, it's a system of conjectures. Mathematically speaking, they're conjectures about geometry, which had their basis in supersymmetric quantum field theory, and later turned out to be closely connected to the exact WKB method and the ODEIM correspondence. So other topics of this workshop. And so my rough plan is, so I'll divide the talk into 2 parts. And the first part will be basically, it should be understandable to a mathematician who doesn't know anything about physics. So the first part is going to be just the kind of geometric part. I'll try to sketch what the program is. And then the second part, I'll say a little bit, because I know there are some physicists here, so I'll try to say a little bit about what is the kind of quantum field theory background of the thing. OK. So that's the setup. So what's the geometry that I'm interested in? So one way to motivate it is to think about think about relativity. Or let's say Calabi-Yau manifolds, kind of Euclidean relativity in the vacuum. So suppose X is a Riemannian manifold with a metric tensor G. So Riemannian manifold. Then, as probably as many of you know, there's a famous equation, Einstein's equation. Okay, this is Einstein's equation in Euclidean signature, which says that the Ricci curvature of the metric is 0. I write it like this because I cannot really, in finite time, write the actual equation. So concretely in local coordinates, G is some symmetric 2 tensor. This Ricci curvature is some complicated function involving this G and its derivatives. It's quite complicated to write it concretely, and so this is some kind of hard nonlinear PDE. It becomes easier if we assume that X is not just Riemannian, but actually it's complex. So let's suppose that it's a complex manifold and that the metric is Kähler. So it's a complex manifold, and the metric is Kähler, but I won't say exactly what Kähler means. I'll just write Kähler. And one concrete sense in which it's easier is that now I can actually write what the equation is. So then the equation that the Ricci curvature is 0 becomes equivalent to the equation that del bar of the log of the determinant of G. So now I write G as Gij bar, because now I have kind of holomorphic and anti-holomorphic indices. So G you can write as a matrix Gij bar. You take the log of the determinant, and then del bar of that should be 0. So that's the Einstein equation for a Kähler manifold. It's still hard, And a measure of how hard it is so there's a theorem due to Yao. And the theorem of Yao is just that compact solutions exist. Well, compact solutions that are not strictly flat. And I don't know the history, but my impression is Yao got the Fields Medal in large part for proving this. Okay, so that's quite a that's somehow a very non-trivial theorem, but Yao's what Yao proves is just that the thing exists. He doesn't tell you anything about what it actually looks like. So if you want to like visualize, this is supposed to be some Riemannian object, you might think you could get some picture of what its geometry is. So Yao doesn't tell you anything about that. And so suppose you want to know what do Calabi-Yau, so these solutions got to be called Calabi-Yau manifolds. And suppose you want to know what Calabi-Yau manifolds actually look like. Okay, so I want to describe one situation in which we can get some handle on what Calabi-Yau manifolds look like. Now, it's not going to be compact, so the very nicest thing would be to do a compact one. The ones I describe will be kind of half compact, meaning that, roughly speaking, it's fibered over a base whose dimension is half the total dimension with compact fibers. So half compact is still pretty hard. And the kind of funny thing is that, so this doesn't look like it has anything to do with WKB, but it'll turn out that the way we produce these Calabi-Yau manifolds is going to have to do with exact WKB. So, okay, so now, so now I shift, in a sense I start again, and now I'm going to talk about Hitchin equations. So now, my geometric data is going to be a Riemann surface, compact Riemann surface. So a complex one-dimensional manifold. Maybe it's this. And we write down a PDE living on this surface. So we're going to write down an elliptic nonlinear PDE for the data of a pair, A and phi. And A and phi are just going to be one forms living on the surface, except that they're valued in n by n matrices. I'll say they're one forms on the surface, valued in, I guess, skew Hermitian n by n matrices. And here's the equation. So it's a set of equations. So d phi is 0. I have to say what d is. D is the covariant derivative. D star phi is 0. And f, so this A we'll think of as a connection. F is the curvature of that connection. And the most obvious equation you could write would be that the connection is flat. That's kind of the usual thing you think of writing. Here we don't say it's flat, but rather we say that its curvature is equal to the bracket phi phi. So this is these are Hitchin's equations, where, okay, let me provide the supplemental notation. So d, as I said, is the covariant derivative, so it's the usual d plus the bracket with a. F, the curvature, is dA plus a wedge a. And this star thing, that's the Hodge star. In local coordinates, you would think that it's kind of like a 90-degree rotation, like that. Okay, so there's our equation. This is Hitchin's equations. It might look a little abstract, so let me write one kind of concrete, the simplest non-trivial example of this to kind of have in your head. Oh, this is the place that I can't write, right? Or if I raise it, it's okay? Okay, let me try writing a little bit over here. So one nice example is to take C. So in general, it was some Riemann surface. But actually, I could just take CP1 and put a singularity at one point with some boundary condition. And I won't be too sharp about exactly how you do that, but I'll just give you an example of it, because that's the very simplest class of examples. And let me write, this part of the story is going to depend on just a complex polynomial. So let me write the polynomial z cubed plus a constant. Z cubed plus a complex number. Doesn't have to be that. It can be any polynomial, but it's the simplest one. And then my phi that I have over there, let me write a kind of ansatz for it. It'll look like this. So the ansatz depends on a function u. And then the whole equation is going to boil down to just an equation for this u, which is an actual function. So the equation, in general, is some complicated matrix equation, but in some cases, it just becomes an equation, for a function. Okay, so here's my phi, and my A is also something concrete. So these are just 2x2 matrices that are built from the data of this function u. Okay, so here's phi and here's A, some concrete 2x2 matrices. And then star, the Hitchin equation, becomes equivalent to the equation Laplacian of u minus 4 times e to the 2u minus e to the minus 2u times the norm of this polynomial squared equals 0. So here's the equation. So this u is just a function in the complex plane. This is just an equation for that function. So I guess if p was 1, if the polynomial was 1, then I think this is called the Sinch-Gordon equation. So this is some kind of this is some perturbation of Sinch-Gordon where you have a polynomial here. Anyway, so that's kind of the most baby example of what Hitchin's equations are. But in general, it's that kind of thing. It's some elliptic PDE on your surface. Okay. So I'll just keep that there, maybe. And now, so now, what does all this have to do with Calabi-Yau manifolds? So I first talked about Calabi-Yau manifolds. Now I'm talking about Hitchin equations on a Riemann surface. Oh, right, this is yeah. So the relation is like this. So let's consider a moduli space, all right, M of C comma N, which is just the space of all the solutions of this equation. So the space of solutions of Hitchin equations, star, modulo gauge equivalence. So there's, if you have one solution of this equation and you have a g, which is a function valued in n by n matrices, you can always make another one like this. So I want to consider the space of all solutions modulo this equivalence. And it turns out if you do that, then you get a nice, non-empty finite dimensional manifold. This space, it's not only a manifold, but it has a natural metric, L2 metric, which I could write like this. So if I have a tangent vector to the space, that's like a little variation of the solution. So to give a metric, I should tell you what's the norm of that variation. And the norm of that variation is just, well, it's the L2 norm, so you literally take just the norm of the variation of phi and the norm of the variation of A. So that's something pretty concrete. And then, oh, fantastic, thank you. And then the kind of remarkable fact, it was discovered by Hitchin, but the complete proof is attributed to various people. So Hitchin, Simpson, Donaldson, and Corlett. The theorem is that this metric, so on the moduli space of solutions of this equation, this metric, oh yeah, so this metric, I call it GL2. Here's its definition. This GL2 is a complete, I put a little asterisk, there's some mild singularities, but let me forget it. So you should think that it's a complete hyperkähler metric. On this moduli space. What does hyperkähler mean? Well, okay, it means the space has a lot of different complex structures and it's Kähler for all of them. But in particular, a consequence of being hyperkähler is that it's Calabi-Yau. So if we want to make Calabi-Yau manifolds, here is a concrete way of making a Calabi-Yau manifold. You take a Riemann surface, you look at all the solutions of this equation, and those form for you a Calabi-Yau manifold. And so now the question is, okay, if we want to understand Calabi-Yau manifolds concretely, now the question is, how concretely can we understand this L2 metric on the moduli space of solutions of this equation? Okay. And so we want to compute it concretely by kind of integral system methods. So, question: what is GL2? And to be really concrete, over here, we've got a family of solutions of this equation parameterized by this one complex number C. Oh, I didn't say, but this equation has a unique solution with some natural boundary condition in infinity. So there's a unique U satisfying this equation, and you can ask, for example, in our example over there, you have the L2 metric restricted to that locus. That's just some function, g cc bar of c dc squared. And so you can ask, what is this function? That's a kind of concrete example of the question. Okay. So how are we going to do it? How can you conjecturally do it? So this is where WKB comes in. So we're going to use WKB, but it's not going to be, maybe the first thing you would think is that you're somehow going to use WKB directly on the Hitchin equations. That I somehow don't see how to do. I mean, partly because there's no parameter here. So, WKB, usually you have a one parameter family of equations, right? And you try to do something in the limit as the parameter goes to 0. So you don't quite see how to do that directly here. But there is a cool thing you can do. So this is the part. It's exact WKB. So we do the following thing. So suppose we're given one of these solutions. Suppose someone somehow gave you one of these solutions. Then you can do the following thing. So this connection A, remember, is not flat because its curvature obeys this equation. But now you say, OK, well, I'm going to consider another connection. I'll write a script A. The straight one was unitary. This one will not be unitary. This is going to be some complex connection. And the way that you make it is you say, OK, well, I'll take, and I'm going to have a parameter, a C star valued parameter. So the family is just, I take zeta inverse times the holomorphic part, let's write phi z dz, the holomorphic part of phi, plus my original connection, plus zeta times the anti-holomorphic part of phi. Oh, this is wrong by an I. OK, I think I make it correct by putting I here and I here. Sorry. Sorry, I don't usually write it this way. Yep, I think this is correct. And this, now what Hitchin's equations say, in fact, they're equivalent to saying that the connection, so now I could consider the connection d plus script dA of zeta, that connection is flat. In other words, this differential equation, d plus script dA of zeta of psi equals 0, that's integrable on the surface for every value of zeta. So now we have this one parameter family of equations. They're linear equations. They're somehow linear equations that are associated with this original nonlinear thing. OK. And now the game is going to be to apply WKB ideas to this family of equations. OK. Well, and fortunately, so it's maybe not 100% obvious, but it's true that if you know these connections concretely enough, and what I mean by knowing them is it'll be enough to know their monodromy data. So, so knowing the monodromy data for these connections, d plus script dA of zeta, for all zeta in C star, that's sufficient to write down a formula for the metric that you're after. Okay, so now our problem is to understand somehow the monodromy of this family of connections. Okay. Okay. Well. So now we're gonna study it by expanding around zeta equals 0. But now is the moment where I have to become. So far what I told you is just facts, but now I have to tell you, something slightly conjectural. So you recall how the WKB method is supposed to work. So the idea is to build solutions of the equation d plus script dA of zeta psi equals 0, build solution psi. Well, generally not global solutions, but at least local solutions. And you build them in the form, a little schematically, you build them in the form that psi of z is supposed to be the exponential of some integral. So think of zeta here. Zeta is standing in the place that h bar usually stands if you had like a family of Schrodinger equations. And so correspondingly here, we'll have 1 over zeta times some integral. Integral up to z, beginning at some z naught, of a 1 form. And that 1 form, I just write lambda of zeta. That's kind of the general structure of the WKB ansatz for Schrodinger equations and also here. Where, now in the exact WKB, which is the model we want to follow here, this 1 form, so for example, in Schrodinger equations, you would get this 1 form by trying to solve the Riccati equation, right? The Riccati equation you can solve formally to every order in h bar, and so here it'll be a parallel thing. You'll be able to solve it formally to every order in zeta. And then there's the non-trivial thing of actually resumming it to get an actual honest 1 form. And so here, we'll say lambda of zeta is obtained in that way. So it's obtained by Borel summation of the formal WKB series. But this is the point where I'm not so sure that this Borel summability is a theorem, in exactly the context that I'm in here. But nevertheless, let me build. I'll just build for you the conjectural picture. So the conjectural picture is okay. This thing indeed exists, and so the local solutions exist. So conjecture these psi of z indeed exist, local solutions, away from the Stokes graph. So the usual picture is that it's Borel summable away from some codimension 1 graph that you draw on the surface. And it's a similar thing here. And the Stokes graph is computable. And it's computable. If you want to know exactly what the Stokes graph is, you can determine it from the data of, essentially what you need is you need to know the eigenvalues of this phi z dz. So maybe I draw a picture of that. So I think similar pictures, of course, appeared already in this workshop, particularly in Philip's talk yesterday. He drew a lot of Stokes graphs. But for example, so we could do it exactly in this situation. So in the baby example above, if let's say let's take C to be 1 and zeta to be real and positive. So one of the tricky things in this business is that you're doing this, you're going to do this WKB, but you want to do it for complex values of the parameter zeta. And then, well, I guess people know this very well. The shape of the Stokes graph depends on the argument of zeta. So it's really kind of a one-parameter family of Stokes graphs. But a typical thing that it would look like, so here if C is 1, the Stokes lines are emitted from the zeros of this polynomial. So maybe I take it to be -1. So they're emitted from the zeros of this polynomial, which in this case would be the third roots of unity. And then they travel, so in this particular case, they travel out to 5 asymptotic directions. So it looks something like this. Oh, I'm in trouble. I shouldn't have tried to do this on the fly. Right. I think it's like that. So let's see, 5 asymptotic directions, 1, 2, 3, 4, 5. Yeah. So in general, it's some, it's some concrete kind of chamber decomposition of the of your curve that's determined completely by the data of your this matrix phi that enters the solution of Hitchin equations. So in any particular example, you can draw it concretely. And the exact WKB is producing for you on a solutions of the equation on the complement of this graph. And then the local solutions jump. So that's the Stokes phenomenon. As you go across the walls, the Stokes curves in this picture. OK. So the kind of geometric content of this, the way I would like to say it, is so the local solutions are got by integrating this one form. And this one form, if you think about it a little bit, you realize that this one form is actually not single valued on the original surface. It's single valued rather on some covering of it. So this lambda, to leading order, it's the eigenvalue of the Higgs field, this phi z dz. And so this lambda is actually defined on a covering, the spectral curve. And a good way to think of it is that this lambda, what it actually defines for you, is a connection living on the spectral curve. So you've kind of reduced your equation. You started out with a rank n equation on the original Riemann surface, and you replace it with a rank 1 equation living on the spectral curve. That's kind of the geometric, that's one way of saying the geometric content of WKB. So let me write that. So the picture is that you started with the connections d plus script dA of zeta, this one parameter family of connections over the surface. And by WKB, you're replacing them with something simpler. That simpler thing is, well, it involves the data of an n-fold cover, sigma to c. That's the spectral curve. So you have to work on this more complicated space. So maybe if n is 3, maybe you picture it like this. It's a branched cover of the curve, of your base curve. But then, instead of having this rank n connections, so here it was a n by n system, so we call it a rank n connection over the base curve, you're replacing it by a family of rank 1 connections, which roughly I would write as just d plus lambda of zeta appearing there, over sigma. And the payoff of that, as is well known to people working in exact WKB, the payoff of that is that this map, it actually goes both ways. So if you have the data of this family of rank 1 connections over the cover, that's sufficient to determine the monodromy data here. So the monodromy data of this one determines the monodromy data of that one. But the monodromy data of this one is way simpler because this one is just a rank 1 connection. That means taking its monodromy essentially is just comes down to computing integrals, literally integrals over one form. So those are called, in the exact WKB world, I think people call these, the holonomies of that connection, people call the verbose symbols. So let me give them in. So So let me give those a name. So the monodromy data of this rank 1 connection can be expressed as just some functions. I'll call them x gamma of zeta, where gamma is a cycle on the cover. So it's a one cycle on the cover. So you just take all the one cycles on the cover, you take the monodromy of this C star connection, and that's sufficient to determine the monodromy, and so it's sufficient to determine this metric that you're after. Okay, now, so far it's all very abstract, right? How to actually calculate? What I want to do is to actually calculate these functions. So how can I possibly do that? Well, so the picture is that they're characterized by essentially by their analytic properties in the zeta plane. But let me say what I mean by that. So the first thing is that this x gamma of zeta, from its origin in WKB, you won't be surprised to hear that its leading asymptotics as zeta goes to 0 will just be got by integrating the first term of this asymptotic series. So, and the first term is easy to write down explicitly. It comes literally from the eigenvalues of the matrix phi. So these are some computable numbers. They're the periods, if you like, of the spectral curve. So in any example, you can calculate what these numbers are. And so you can calculate the leading asymptotics of this function x gamma. Now, the second thing, and the thing that makes these functions a little bit interesting, oh, sorry, maybe I do it in different order. So that's as zeta goes to 0. As zeta goes to infinity, it's actually essentially the same, because this whole structure has a kind of symmetry between 0 and infinity. That's very different from the usual thing with Schrodinger equations. But here we have a symmetry between 0 and infinity. And so concretely, what it says is that this x gamma is related to x gamma of minus 1 over zeta bar. So it's like the antipodal map on the sphere. Can't be this, it's complex conjugate of this, minus. So this function is piecewise holomorphic in zeta. It has this relation. Okay, and now if you just had 1 and 2, and also you knew that the function was analytic, holomorphic in zeta, then it would be determined by these properties, right? If it's analytic and you know what happens at 0 and you know what happens at infinity, it's analytic everywhere else, then it would be determined to be just the exponential of this period plus its complex conjugate, roughly. That would be too boring, and that's not what really happens. The interesting part, the part that makes this story at all non-trivial, is that the function x gamma of zeta that appears in this exact WKB story is piecewise analytic. In zeta. Okay, why piecewise analytic? It's piecewise analytic because, let's draw a picture. It's piecewise analytic because its construction involves the Stokes graph under the hood. And as we said, the Stokes graph depends on zeta. So why piecewise? It's because as we vary zeta, the Stokes graph, so I'll call it S of zeta, so it varies, and when you change zeta a little bit, the Stokes graph just varies continuously. So it changes like by just essentially a homotopy. But there are some critical moments, some critical phases where the Stokes graph suddenly changes its topology. Can change its topology. So the typical picture is like this. So like in the rank 2 case, the typical picture is you have something like this at one phase. And then as you vary the phase a little bit, this one rotates down, this one rotates up. So there's a critical phase where this happens. So this critical object, let me call it a finite web. So it's when some compact thing appears inside of the Stokes graph at a critical phase. And then at the other side, there's a picture like this. So the topology has changed. Nope. The topology has changed in going from here to here. And correspondingly, these functions x gamma, they suffer some discontinuity. But it's analytic. You can calculate exactly what the discontinuity is. So it's some, in fact, that's a Stokes phenomenon that's suffered now by these functions. So there's a kind of nonlinear Stokes phenomenon for these x gamma of zeta. And in this rank 2 case that I'm drawing here, I think this is also something very familiar in the exact WKB community. So if I understand right, it's supposed to be called the Delabert-Dillinger-Pham formula. That's this nonlinear Stokes phenomenon. But okay, maybe I just advertise a little bit. So one of the interesting things about this story is that you get a very parallel thing, but for all ranks. So where the objects that appear are more complicated than this one, but you can systematically describe what's the Stokes phenomenon induced by any object that appears in the Stokes graph. Okay. So then the picture is finally so the analytic structure of this x gamma of zeta is something like this. It's piecewise analytic in the zeta plane with just discontinuities along some rays. So these are like the Stokes lines for the x gamma, this kind of secondary Stokes lines. But you know exactly where they are. And you know exactly what the jump is across these lines. So then you can try. So having this information 1, 2, and 3, what it says is that at these functions, these kind of WKB monodromies, that they're solutions of some Riemann-Hilbert problem in the plane. So you just look for a function that has these analytic properties. And that Riemann-Hilbert problem then, so now it's formulated without, using just the data of the Stokes graphs and the periods, nothing else. But its solution is supposed to reconstruct for you the monodromy of this family of differential equations. So now the idea is to solve that Riemann-Hilbert problem. Once you solve it, then you get the Calabi-Yau metric that you were after. And so this you can actually do. So certainly, in general, it's a conjecture that this Riemann-Hilbert problem actually has a solution, but you can experimentally solve it. So for example, you carry out this program in the case of the solutions of Hitchin equations that I wrote implicitly over there, and then you calculate this GCC bar, the metric. For example, if you calculate it at the point c equals 0.5, you get that it's 25.061. And then you go and you actually solve Hitchin's equations numerically on the computer, and you calculate the L2 metric, and sure enough, it's 25.061. So I just want to say, I'm describing all this as conjectures, but I don't want to make it sound sort of too conjectural. I mean, there's something that really works. Okay. Okay, so that's as much as I wanted to say about kind of what the general program is and how it's related to exact WKB. And then maybe in the last little bit, I'll say just a little bit about where it came from. So this is now for the enthusiasts of supersymmetric quantum field theory. So the setup is like this. So what was the main player in my story? The main player in my story was really this Riemann surface, right? So now I'll just write a little dictionary. So starting from a Riemann surface C, there's a construction of a particular quantum field theory, but not a quantum field theory living on C. So the quantum field theory, so it's a so-called n equals 2 supersymmetric quantum field theory. Some particularly nice kind of quantum field theory, which lives in 4 space-time dimensions. Sometimes it's called class S theory. So I'll call it T of C. And somehow everything that we're doing in this story, we would interpret as some statement about this 4-dimensional quantum field theory T of C. That was, in fact, the original motivation. So in what I was telling you, I was studying the monodromy, or you could just say the parallel transport of the connections A of zeta along paths in the Riemann surface. So what's the kind of physics meaning of a path in the Riemann surface? So let's call the path P in the Riemann surface. And then for technical reason, we also need the data of zeta and C star. That data together is supposed to produce for you something in this four-dimensional quantum field theory. And what is it? Well, it turns out to be it's a kind of operator in that quantum field theory. But to be exact, the operator it's actually an interface. So I'll call the interface LP. So let's say P is a path. Here's my path from Z0 to Z1. So this is a picture inside of the Riemann surface. And what it produces for you is an interface between two surface defects. So I'll call them SZ0 and SZ1. So the picture is we're in four dimensions, but now we study a surface, some kind of operator that lives on a surface. And the surface is divided into two pieces. One piece is labeled by this point Z0. Another one is labeled by this point Z1. And in between, there's an interface, and that interface is determined by the path. So the way that we see this Riemann surface, in a sense, is the Riemann surface itself is a moduli space. It's a moduli space of these surface defects. And in that context, there's no particular reason why C had to be one-dimensional, by the way. So it seems that there should be a similar story in higher dimensions, provided that you consider, it'll be kind of very integrable kind of equations in higher dimensions. So I don't know to what extent that's sort of studied in the exact WKB world, but it seems, and we didn't study it much, but it seems like a natural direction for this. Anyway, so this is the, so that's what a path is supposed to mean. And now, so let me write just a little more of the dictionary here. So another important player in this story was an n-fold covering. What was the spectral curve in the geometric story. And what that corresponds to in this four-dimensional quantum field theory is it's the data of a vacuum. Let's say a generic vacuum. So for the professionals, I'll say it's the Coulomb branch of this theory, T of C. So these highly supersymmetric field theories, they tend to have not just one vacuum, but a kind of degenerate family of vacua. And so here, choosing one specific vacuum corresponds to this choice of a spectral curve. Yeah, so in the n equals 2 ology, this is sometimes called the Seiberg-Witten curve. Okay, and then maybe the interesting part is what's the meaning of the Stokes phenomena in this language of the n equals 2 theory. So suppose that I now have, my path, and here I have a Stokes curve. So the Stokes curves, once I fix sigma, that completely determines the topology of the Stokes graph. So I can ask, what does it mean for this path to move across the Stokes curve? So let's be sharp. Let's say, suppose this point moves across the Stokes curve. Move Z1, one of the endpoints of my path. What does it correspond to? Well, what it corresponds to is a wall crossing phenomenon. Wall crossing for what? So here we've got a picture of a interface connecting two surfaces. That's a one-dimensional system. So one-dimensional quantum field theory is like quantum mechanics. You can think of this is just some quantum mechanical system that we're studying. And you can ask, then it's meaningful to ask, like, what's the Hilbert space associated with that quantum mechanical system. In particular, let's not ask about the whole Hilbert space, that's too hard, but let's just ask about the ground states, the lowest energy states. So it has some finite dimensional space of ground states, but if you ask what exactly is the space, well, the answer depends on where exactly you are on the surface. So, and the statement is that the Hilbert space of ground states of this interface defect, LP, it jumps. So it either gains or loses some states. That's the wall crossing phenomenon. And how does it jump? So what's the physics picture of how it jumps? The physics picture of how it jumps is that there are some states. So you make a you can make a rough kind of semi-classical picture of what the states look like. And the idea is that some of the states you can think of as kind of a bound state where you have some excitation that lives here, and it's bound to an excitation that's like a bulk particle that lives on this surface defect. And what happens is that as Z1 approaches the wall, that bound state becomes more and more loosely bound until it decays right at the moment when you hit the Stokes curve. So, in other words, you would say a state can decay, and the way it decays is by emitting a bulk particle living in one of these two surface defects. So it's like it emits something going this way. That's because I moved Z1 across the wall. Then it has to do with particles that live in the Z1 half of the picture. Okay, so then there's, in some sense, all the Stokes phenomena in the story get explained in this kind of way, or get interpreted in this kind of way, that it's always some bound state that decays by emitting a particle. But in the story that I told, I described two different kinds of Stokes phenomena. First, there were the simple linear ones that had to do with the walls of the Stokes graph. That one I just said what it is. Then there's the nonlinear one that had to do with the appearance of this finite web, right? When the topology of the Stokes graph changes. So that one also has an interpretation like this, but a little different. So, okay, maybe I draw it over here. How am I for time? I'm almost done, right? Okay, maybe I just say this last thing and then I'm done. Well, yeah, I won't even draw the picture. We'll just write. So, other Stokes phenomena. So all the Stokes phenomena in the story somehow are similarly associated to states in the Hilbert space decaying. And so, I'll just say in words that I think this, you could ask which part of this story should be interesting, for people that are interested in exact WKB, but not interested in four-dimensional supersymmetric field theory. I think there's two possible answers. So, first, there's a kind of technical answer, which is, at least for me as a consumer of this theory, I would be very, very interested in knowing to what extent the picture that I described can be made rigorous. So, and it's particularly about this question of the Borel summability of the local solutions. First of all, in higher rank, and second of all, in this setup where the family of connections that we have is not exactly, they're not exactly opers. It's some more general family of connections. So that's a technical question. The more conceptual thing, which I think should be interesting, but I couldn't tell you exactly the mathematical framework today, is that, in this picture, the Stokes phenomenon associated with this wall, what it has to do with in quantum field theory, it has to do with this bulk particle, the state of a bulk particle that can decay. And so the thing about it is that this is not just a number. So usually you would say on this wall there's some Stokes factor associated. But here what there's associated is really not just a number, but it's rather a vector space, right? It's the space of states of this bulk particle. So that's a vector space whose dimension is equal to the Stokes factor here. So in this context, I think it's well known that for these linear ODs, right, the Stokes factors are quantized. They're integers in kind of natural units. But here that integer arises as the dimension of some vector space. So the whole story, in some very loose sense, should be thought of as categorified. Okay, so that's some mathematical structure which might be interesting in the future. So, and there's some work in this direction. There's a paper of Gaiotto, Moore, and Witten where they started to develop some aspects of what that kind of categorification looks like. Okay, so I think I better stop there. So, thanks.
Any questions? Over there?
So I have a question. I haven't understood exactly what is the relation between the metric and this.
Oh, and the monodromies.
And the monodromies.
Yeah. So, right. I didn't say. I just said that you can calculate it. But the one way to say it is like this: to know the hyperkähler metric. So what's a hyperkähler metric? So you have the metric. You have 3 complex structures on the space. And then you have 3 Kähler forms corresponding. Now, so to know the metric, evidently, it's sufficient to know these Kähler forms. Now, if you build a complex combination of these Kähler forms, say omega j plus I omega k, that's actually a holomorphic symplectic form in structure I. And so it's sufficient to be able to calculate these holomorphic symplectic forms. And those, as it turns out, there's a very direct formula for them in terms of the abelian monodromies. And the formula is, so more generally, we have a family of complex structures labeled by zeta. So I'll write the holomorphic symplectic form in structure zeta, called capital omega of zeta. It turns out it's just, so let's take a basis of the homology of the spectral curve. So gamma 1 up to gamma 2n. And then it's just you take d log of xi wedge d log xj times epsilon ij, the intersection pairing between I and j. So sum over I and j from 1 to 2n. So it's, this is I guess the somehow mathematical name for this symplectic form is it's the Atiyah-Bott symplectic form, or the Goldman symplectic form on the moduli space of connections. And the kind of cool thing is that this map is actually a symplectomorphism for that holomorphic symplectic form. So the thing you need to do is to calculate it here, but it's much, much easier to calculate it here because the symplectic structure here is very simple. It's just given by the intersection pairing of the cycles. And so that's what you in practice do. And once you have these holomorphic symplectic forms, then the metric is algebraically determined by the holomorphic symplectic forms.
But at the beginning, you didn't have the z.
What's that?
In the starting from itching PD, etc. You didn't have the z.
No, that's right. That's right.
So the metric didn't.
It's a non-trivial theorem about this metric. That's right. So the metric, I wrote for you the formula for it just as L2 metric. It's a non-trivial fact about that metric that it's actually hyperkähler. And for that reason, it can be computed in terms of these holomorphic symplectic forms. But I agree, it's not. So I'm telling you the formula for the holomorphic symplectic forms. Okay, then if you literally want the metric, okay. So what's the formula for the metric in terms of this data? One way to write it, some crazy formula of hyperkähler geometry. You have 3 forms, and you write omega I, omega j inverse omega k. So if you literally want to get g from this data, that's one formula that produces for you the g. Yeah.
Thank you.
Can I continue David's question? But how can you just give an idea on how do we show that this metric here is the same metric that you have defined in terms of the equation data?
Right. So, yeah, so it goes in a few steps, right? So Oh, I see. No, you're talking about just Hitchin's story, not anything about this WKB stuff. Yeah, so it goes, I guess the key thing is the observation that these, so I can't tell you the complete proof, but let me tell you what's the kind of basic structure of it. The Hitchin equations that I first wrote, now erased, the Hitchin equations that I first wrote were like d star phi is 0, d phi is 0, and f plus the bracket of phi and phi is 0. And so these equations you can think of in the following way. You start with the space of all possible forms A and phi. That's just a massive linear space. Okay. That space, as a linear space, it has a kind of simple hyperkähler structure that you can write down. Then these equations get understood as the hyperkähler moment map. So the idea is you have this hyperkähler space, and then there's a construction called hyperkähler quotient. So it's kind of hyperkähler version of the usual symplectic quotient, symplectic reduction that you do like even in classical mechanics, right? So these three quantities, I wrote them as just some equations, but they arise as the components of the moment map. And so for that reason, the quotient acquires a hyperkähler metric, and that hyperkähler metric is sort of essentially just comes from the original hyperkähler metric here. That's why it's given by the formula that I wrote. So I wrote some very simple looking formula, which is just the formula in terms of the original linear objects. Once you know that, so then you know that this metric is hyperkähler, then, then there's some general hyperkähler geometry, which I won't be able to kind of quickly reproduce, that says that you can compute the metric from the three symplectic forms on this hyperkähler space. Maybe I can show you more. I don't think I can do it in 1 minute.
Okay. Interest of time, I think further questions should be over coffee. Let's thank Andy again. One more announcement. A set of taxis to various airports and railway stations and whatever have been made. So if you're in that situation, please talk to somebody at the reception as soon as possible to get all the details. Okay? Oh.